Hi class, welcome to lesson 35. In this lesson, you are going to use the VSEPR theory to determine the three-dimensional shapes of covalent molecules. Recall that ionic salts have a crystal lattice structure. The three-dimensional shape of a covalent molecule is determined by the VSEPR theory, or the valence shell electron pair repulsion theory, which states that negative electrons arrange themselves so that they can minimize their repulsion around a central atom. We have already used the VSEPR theory to determine that symmetric molecules are nonpolar and asymmetric molecules are polar. Remember the acronym SNAP. When using the VSEPR theory, it is important to distinguish between bonding pairs of electrons and non-bonding pairs of electrons. Bonding pairs of electrons are typically written as a line in the Lewis electron dot structure, while non-bonding pairs of electrons are pairs of electrons that do not make bonds, but are still important as they help the elements complete their octet. The four major shapes of covalent molecules that you will need to know are the linear, bent, pyramidal, and tetrahedral shapes. Take a moment to pause the video and copy down this chart. We will then work together to explain each part of this chart so that you can correctly identify the three-dimensional shape of covalent molecules using bonding pairs of electrons and lone pairs of electrons around a central atom. A linear shape is a three-dimensional shape that results when only two atoms are bonded. In this carbon monoxide, you can see that this linear molecule is asymmetric as carbon is different than oxygen. So this is a linear molecule that is polar. Asymmetric is polar, according to SNAP. The only way to arrange two items as far apart from each other as possible is to arrange them 180 degrees apart. Thus, we have the linear shape. Some linear molecules will be nonpolar. Nonpolar linear molecules result when you have only two bonded atoms, but those atoms are identical, like in oxygen. Oxygen is linear, and it is nonpolar because it is symmetric. Remember, SNAP. Carbon dioxide is another linear, nonpolar molecule. The central atom of carbon dioxide is carbon. It has two bonding groups as it is bonded to two different oxygens, and it has 0 lone pairs of electrons. When you have two bonding groups and no lone pairs, you will always have a linear shape. Both of these molecules are perfectly symmetric. Remember that symmetry makes these particles nonpolar. Bent shape is the result of having two bonding pairs of electrons and two lone pairs of electrons around the central atom. In this case, we have water. Notice that the non-bonding electrons take up space, thus causing the bent shape for the entire molecule. Water lacks symmetry. Since water is asymmetric, it is polar and bent. The other shape that we can have is a pyramidal shape. The pyramidal shape is seen here in ammonia, where we have 3 bonding pairs of electrons and 1 lone pair. Ammonia has a pyramidal shape. Although there is a vertical line of symmetry, there is not a horizontal line of symmetry. So ammonia is asymmetric. Applying the acronym SNAP, asymmetric is polar. So ammonia is pyramidal and polar. Whenever the central atom has 4 bonding groups and no lone pairs, you will have a tetrahedral shape. Here we have methane. Methane has a tetrahedral shape. Methane is symmetric on both the vertical and horizontal axis. Applying the acronym SNAP, symmetric means methane is nonpolar. So methane is tetrahedral and nonpolar. Again, we are back at the chart that you should have copied down at the beginning of the video. Make sure that you have copied down this chart so that you can use it for a reference as you are studying. Let's look at a practice example. Here we have carbon tetrachloride. If we wanted to determine whether or not this molecule is polar or not, we can examine the last subscript. That is the subscript attached to the chlorine. The subscript is 4. 4 is even, meaning that we are going to have a symmetric molecule, and carbon tetrachloride will be nonpolar. If we draw out the Lewis dot structure, we can examine what will happen with its three-dimensional shape. So its three-dimensional shape has 4 bonding groups and no lone pairs around the central carbon atom. That means carbon tetrachloride will be tetrahedral. And again, we can examine both the vertical and horizontal lines of symmetry to see that it will be nonpolar. So carbon tetrachloride is both symmetric and tetrahedral. Let's look at the example of dihydrogen monosulfide. Here, looking at the last subscript, we're going to look at the subscript for sulfur. Since no subscript is written, the subscript of 1 is understood. The number 1 is odd. That means that we are going to have a polar compound because it will be asymmetric. Now, if we draw out the Lewis dot structure of our asymmetric and polar molecule, what we can see is that there are 2 bonding groups around the sulfur and 2 pairs of lone electrons. That gives this molecule its bent shape. So dihydrogen monosulfide is bent, asymmetric, and polar. So by now you should be able to use the VSEPR theory to determine the three-dimensional shape of a covalent molecule. This concludes lesson number 35 on molecular shapes. Make sure you've taken good notes and bring them to class so that you can revise and add to them. Write down any questions you have in your notes and ask them in class. Complete your homework on Google Classroom and put your Regents Chemistry reference table and calculator back in your backpack so you are prepared for class. I'll see you soon.